on last week we started looking at spin one fields. So we came up with some kind of a Lagrangian. This was the Lagrangian, which is, this is the core, sorry, not there. This is it. This is our Lagrangian. Now compare it with the scalar Lagrangian. You see, here we have the scalar Lagrangian. Look at the signs. You see, one problem is always the signs of these terms. If you look at the mass term, it's a negative sign. And when you calculate the energy momentum tensor, you see here, well, the energy momentum tensor has a lower energy. Then we go to the vector fields. And if you remember last week, I took the sign minus, the negative sign for the mass squared term. And we ended up having such an energy density with minus 1 over 2m squared a0 squared and minus 1 over m squared a squared, which definitely doesn't have a minimum of energy. It's not bounded from below, which practically tells us that the sign I chose to start with in my Lagrangian was wrong. So the signs are not that arbitrary. Okay, there are always conventions. We are free to define the conserved any conserved charge up to a sign, up to a constant, in fact. You can just define anything. Well, you try to agree with the general conventions, and in the general conventions for the vector field, the sign of the mass squared term in the Lagrangian is not negative but positive. But actually that's a negative. Okay, what do I mean by actually that's the negative? Remember what we had done. We are trying to write down the Lagrangian for a spin one field which has 3 degrees of freedom. So in particular, we should have 3 fields describing each degree of, one field describing each degree of freedom. But if we use a 4 vector, which makes the Lorentz symmetry obvious, let's say, then we have 4 fields instead of 3. One of those fields is superfluous in the sense that, at least in this Procol Lagrangian that we derived, the A mu field has to satisfy del mu A mu is equal to 0. And del mu A mu is equal to 0, well, we will also go over this today, basically means in the rest frame of the particle, there is no 0 component of the particle. So essentially, the propagating components, in a sense, are not the 0 component, but the other components. And keep in mind that A mu squared is A0 squared minus A squared. The coefficient of the mass squared term for these fields, which are the actual propagating physical fields, is still negative, just like for our scalar case, minus 1 over m squared over here. Now, if you correct those signs, at the end of the day, you have an energy density up to total derivatives. The energy density just becomes the sum of positive terms only. And hence, we have a positive definite energy density, or an energy density that is bounded from below, let's say. And in fact, if you just set m is equal to 0, you see here you basically recover the energy density of the electric field and the energy density of the magnetic field. So any questions up to here?
You say that the vector potential is the real propagator of the field, but scalar.
I'm not strictly saying that, but in the rest frame, it is only the space components that remain. Yes, only the space components that remain. That's what I'm saying. Of course, in other reference frames, you have all the 0 component and the space components, but for each excitation or for any state, let's say, you can always go to some specific frame in which the space components, or what corresponds to the space components in the rest frame, they will have 0 component and space component in another reference frame, but still the number of degrees of freedom will be 3. Just moving to a different reference frame didn't give me a new degree of freedom. Won't give me a new degree of freedom. But we will have problems. We should keep in mind and we should eventually address. Sure.
Contraction of four vectors gives mass, but for potential.
Hold on. What do you mean contraction of four vectors?
Contraction of momentum gives us mass, but contraction of four vectors. It gives also mass, but.
Why? You see, momentum is a special case. It's a special four vector. Its square is just mass squared. That's it. So let's look at our Lagrangian. And of course, we can always go to the momentum space. Well, the equations of motion will be, in fact, the original equation of motion that we derived was this one. This is equal to 0. Then we said that if this equation is satisfied, if I take the derivative once more, the first two terms will cancel, and we will end up having m squared del mu a mu is equal to 0. And if m is not 0, del mu a mu should be 0. So this is again a result of the equations of motion. It's not an additional condition we impose. If we have a field that is governed, whose properties is governed by this Lagrangian, its for divergence has to be 0. And if the for divergence is 0, we have del plus m squared a mu is equal to 0. Now, what do we do for quantization? Well, we already know the equation, the solutions for this. I can quantize that field by writing, I can try at least, d cubed k divided by 2 pi cubed, 1 over twice omega k, ak. Now remember, I have 3 different modes. For a given k, I can have 3 different particles, essentially, corresponding to different polarizations. AKI, let's say epsilon mu, this is the polarization vector, corresponding to the 4 vector k, I, e to the power I k x, and then we have the creation operator. And remember, these A fields are real fields. Since they are real fields, those two operators, this one and this one, they have to be the conjugate of each other. Otherwise, it won't become a real field.
There has to be also some override, right?
Yes. This will be my field. Now, what are these vectors? Well, let's look at this a mu ki. Now, to study these polarization vectors, let's go to a special reference frame. Let's go to the frame in which k is whatever energy it has, or omega k, 0, 0, k. And so we are in a reference frame in which this k is we are choosing the z-axis to be in the direction of the space component of this k. Now, what are these omega mu i's? Remember, omega mu del mu a mu should be equal to 0, which...
Meaning this lower of the energy density is chi, or do you...
What do you mean energy?
Just the, right below energy density kk in parentheses.
E is equal to omega k.
Yeah, I understand that.
That's not energy density, that's just the polarization tensor.
Epsilon is the polarization tensor. This is the polarization tensor. this one.
Hocam, why are we summing over different I?
Well, because you see, I'm trying to write down the most general solution of the equations of motion. A mu can have three different polarizations, and each one can have its own function, its own coefficient. So this is the most general solution of the equations of motion. Now, this is the most general solution of this equation of motion. But I have an additional constraint, this one. I should also impose that one, which restricts the possible values of the polarization vectors to k mu epsilon mu I is equal to 0. You see, a mu is a 4 vector, so I should expand it in terms of 4 vectors.
Polarization tensor symmetrical answer.
This is not a tensor, this is a vector.
Polarization tensor.
A mu is a polarization vector. There's no tensors over it. I have 3 of them. In principle, I have 4 of them, but not all of them satisfy this condition. I should only use the polarization vectors that satisfy this condition. Now, for this special case of k, one possible choice of these 3 vectors would be this one. Let's say polarized in the x direction, polarization in the y direction, or polarized, let's say, in the z direction. Or this is usually called the longitudinal polarization. Well, another choice, well, the longitudinal polarization is kept as it is.
What do you mean by 1 over Z?
Hmm?
What do you mean? 1 over M, right?
This is another choice. Now, first, let's look at these two. What do they represent? You see, we were discussing about the spin. Let's see how does those two polarizations behave on the rotations around the z-axis. Let's say that initially I have some polarization in this direction. When I rotate it by an angle theta, it becomes this vector. And we had already seen that epsilon prime vector should be e to power minus I theta sz epsilon, whatever sz is. Sz is, no, not whatever sz is. Sz is the spin of this system. Now, I already know how these vectors, these 3 vectors will transform. I know that epsilon x prime will be epsilon x cosine theta minus epsilon y sine theta, and epsilon y prime will be epsilon y cosine theta plus epsilon x sine theta for this epsilon plus. Remember, this is 0, 1 plus I 0. What you would get is epsilon x prime will be 1 over square root of 2 cosine theta minus I sine theta. Here there is a 1. This one is nothing but my epsilon x. This I is nothing but my epsilon y. So that is epsilon x. This is epsilon y. So this just becomes 1 over square root of 2 e to power minus I theta. This is my epsilon x prime. Similarly, if you calculate epsilon y prime, this will be 1 over square root of 2. Now, epsilon y for this plus polarization is I cosine theta. Epsilon x is 1 sine theta. Well, if you take out the I, this becomes I over square root of 2 e to power minus I theta. So epsilon plus mu let me put a prime, epsilon prime plus mu is just 0, 1 over square root of 2 e to power minus I theta, I over square root of 2 e to power minus I theta, 0. This is e to power minus I theta, epsilon mu plus. So on the rotations, what we define as epsilon mu plus just acquires such a phase. Well, that basically tells me that Sz acting on epsilon mu plus should be plus epsilon mu plus. So it's a spin 1 object, as it should be. We had already seen that vectors are spin 1 objects. So this polarization is the polarization for a photon that has plus 1 helicity. Well, you can basically repeat the same operation, and show that Sz acting on epsilon mu minus will be minus epsilon mu minus. What will change? Well, you see this sign will change over here because epsilon mu minus has the minus I, not plus I. But if this sign over here changes, that would change that sign over in the exponent. Well, that means the Sz acting on my polarization vector has to be minus the polarization vector. And finally, Sz acting on epsilon mu, the longitudinal polarization. Remember, I'm looking at rotations around the z-axis. So if you look at the longitudinal component, longitudinally polarized vector, well, there's no x and y components. X and y components are 0, but it doesn't change. This is 0. So this is called positive helicity. This is called negative helicity. Now, what is helicity? Remember, my particle is moving in the z direction, and I'm looking at rotations around the z-axis. So I'm basically looking at the component polarization of spin along the z-axis. So that is what we call the helicity.
Can I ask something?
Yes?
Did we pick any normalization for the polarization vectors?
Hmm?
Did we pick any normalization for the polarization vectors?
Well, if you look at the polarization vectors I chose over here, epsilon squared for all of them is minus 1. They are negatively polarized. So basically it's the direction. It's a unit vector, essentially. Y minus 1 in the rest frame, you see, if we are in the rest frame, that means k is equal to 0. K would be 0 in the rest frame. There's only the space components. So what is the direction of the polarization vector? That is just the unit vector pointing in the direction of the vector potential.
Can I again ask something? I don't know whether it's like chicken or the egg kind of
Mhm.
situation, but since we find plus 1 helicity, it basically boils down to our normalization condition on the polarization. It doesn't.
You see,
Whenever I
Sz,
look for the polarization vector, I always get this plus 1 or plus something.
whatever lambda is, this will always be satisfied. Change the normalization, and still you have, this is what determines the helicity, the eigenvalue of Sz. So normalization doesn't have any effect on the definition of helicity. So let's say that eventually we will be doing perturbation theory. What else do we need to do for the perturbation theory? What do you remember? How did we, we quantize the field. This is this is square root. This is my quantized field. We have the AK dagger, they are the annihilation and creation operators. And what else do we need to do perturbation? I mean, when we have interactions to calculate in the theory, we use perturbation theory, but we need some ingredients, right? Like the two-point function or the propagator. Well, we can define the propagator here. Now, this time the propagator will be written in this form. So what will this be? Well, of course, one way of calculating this one will be just use the expansion of A mu and A nu in terms of annihilation creation operators and try to just sum it up. Or another method will be just let's determine the differential equation that this object satisfies. Let me call this the mu nu f x and y. What is the differential equation satisfied by this object? Well, we would guess that A mu satisfies this equation. Let me just try to act on this object by this one. And this, what will this be? Let's show it. Will it be the Dirac delta? Well, remember, okay, there will be at least one term that will come from, let me call that operator L. L acting on A mu of x, A nu of y, plus there will be other terms. This will be 0, because A mu satisfies that that operator acting on A will give me 0. This is alpha. The reason why I put mu and alpha is, let's see, this is what I'm looking for. And this mu and alpha are basically independent. I'm just trying to use the equation of motion of this one without contracting to A alpha. But then we had that, if you remember, we had that other problem. The time derivative always gave us the problem. And this operator actually gave us minus I 0 time ordered product x0 minus y0, not this one, plus 0 time ordered derivative of del t A mu x A alpha y. There is no.
In the first line, nu has to be alpha, right? In this first line.
In which first line?
First line, just see. Nu and alpha are.
No.
Okay.
The operator has two indices, mu and nu. The propagator has indices mu and alpha. Alpha is not nu, nu is not alpha. So whatever that object is, we'll still have two indices, nu and alpha.
Okay.
Well, this commutator is, let's just blindly say that is the first one will be the momentum. So the commutator, equal time commutator will be minus I, the three-dimensional Dirac delta x minus y. And so what we will get at the end of the day is plus m squared g mu nu minus del nu d mu alpha x y is equal to minus I delta 4 x minus y. Well, I'm kind of doing hand-wavy arguments over here because you see del nu, it might also give me some additional contributions if mu and nu are somewhat equal to time. If both mu and nu are equal to time, that will give me some additional contributions that will be proportional to my Dirac delta. But that won't be our only problem. So let's stick with this for the time being. Well, the general...
Shouldn't there be something with mu and alpha on the right hand side?
This is g mu alpha, this is g mu alpha. You see, if mu and alpha are different fields and they commute, if mu and alpha are the same fields, they might not commute. Because you see, here I have a field mu, here I have a field alpha.
In the left-hand side, we have nu and alpha because mu's are constant.
So, you see, what I'm looking at is I'm studying this object.
He said on the right side, mu has to be at nu.
Oh, sorry, you are right. This is nu. Because this operator later on will be multiplied by g mu nu.
John, when we brought the box plus m squared inside of the expectation value, are we applying it to the product of a mu and a alpha or just a mu?
We are applying it to the product of a mu and a alpha, but remember, this is the box operator is acting only on x. It's not acting on y. Well, let me also still continue being a bit doing hand-wavy arguments. D mu alpha f x, it will have the Fourier transform d mu alpha p. P is the Fourier momentum, and d mu alpha p should satisfy minus p squared plus m squared g mu alpha plus p mu p alpha d mu alpha p should be minus I g nu alpha. Now the question is, how do we solve such an equation?
I guess there again some problem with the indexes.
Yes.
Alpha indeed.
Yeah, alpha, no?
No, that's
Yeah.
That was all. Okay.
So d mu alpha p, this is some function of p, but it should also be a tensor with two indices. And the only way I can have that is if this has a component proportional to g mu alpha, let me call the coefficient a p squared, another component proportional to p mu p alpha. Let me call the coefficient p, a function of p squared. This is the only option I have.
how did we know that it is symmetric?
I don't. But these are the only two tensors I can write that d mu alpha p can depend on. It just turned out to be symmetric. There is no third term that I can write which won't be symmetric. You see, if you look at d mu alpha p, it only depends on p. The metric is always there. So these are the only two structures. And these two structures turned out to be symmetric. Well, if you put it back, Now let me find the coefficient of G nu alpha on the left. Or let me just multiply it out. Minus p squared plus m squared G nu alpha. This is the product of the first terms. Product of the first term and the second term, there is an a plus minus p squared plus m squared p nu p alpha b. This is the product of these two. The second term multiplying the first term, I will get a p nu p alpha. This is the product of these terms, and the last combination would give me plus b p squared p nu p alpha should be equal to minus I G nu alpha. On the left-hand side, G nu alpha appears only here. So A is I over P squared minus M squared. We had already determined A. On the left-hand side, the coefficient of P nu P alpha is minus P squared plus M squared A.
Second term should be B, not A.
Then, sorry, this is B, right? B. Minus A plus B P squared. This should be equal to 0 because on the right hand side I don't have any P nu P alpha term. So these will cancel. So we get A is equal to M squared B, or B is equal to A over M squared. So now I know what D is. A was I over P squared minus M squared G mu alpha minus P mu P nu
May I ask a question? Can we just go on and where we wrote the equation for A mu, equation of motion A mu. Maybe you. Okay. So.
This one.
Yes, exactly. So in this part we said that when we hit with a partial mu,
Mhm.
the equation is satisfied if and only if m is not 0, we have some kind of a constraint. But that constraint is purely a geometrical constraint that our equation gives.
What do you mean by a geometrical constraint?
So it's actually it comes from the geometry. It's not that we are making a gauge choice.
There's
We
no
are-
gauge here. We are not looking at any gauge symmetry. That is a constraint that my equation of motions tell me that it should be satisfied.
But to be able to solve a mu as a wave, if
Mhm.
this field is not Proca-type, then m will be
Well,
0.
we are looking at the Proca equation. I'm not looking at the case m is equal to 0 yet. I have a massive spin 1 field.
Mass for massive spin 1.
Yeah, that's the thing I'm looking at.
But because it will somehow align with the how we find the propagator, right? Because if m was
You see,
0,
this propagator is wrong. Let me put in quotes. Why? This should be satisfied. But the propagator I chose does not satisfy.
doesn't.
Yeah.
Okay, because we are not making
We did some mistakes.
How did we decide on the form of the propagator? I couldn't understand.
Which one?
You
Well,
said a specific one.
You see, in fact, this was the part that I wanted to discuss. The reason why I calculated that propagator is exactly this one. Because I have an object. I don't know what it is. I want to calculate it. But I know that it only depends on P. and it has to be a rank 2 tensor, meaning it has to have 2 indices. So then I ask myself, what are the structures that the mu alpha, whatever that is, can depend on? That will have 2 Lorentz indices, and it will depend only on P and nothing else. Well, the 2 objects I have that has 2 indices are G mu alpha and P mu P alpha. These are the only 2 objects that depend only on P and the metric. Of course, metric is always there. That depend only on P and have 2 Lorentz indices. So whatever tensor I write, that depends only on P and the metric, should have that form. It should be a superposition of these 2 structures. I don't have any other option. I still don't know what these functions are. The A and P, B are the thing that I still don't know. I have to calculate. But this general structure, I can definitely say. Yes.
But we can also add as many P squares as we like.
Such as? Tell me.
I mean, P squared depends on P.
Okay,
And it doesn't change
Sure.
the tensor structure.
Yeah, I mean, that is why
I think it's a matter of trial and error.
the coefficients
Yeah.
depend on P squared.
That's true.
So this is the most general expression I can have. And then, of course, the question is, what is A, what is B? So we did all these derivations. But there are a couple of mistakes we did along the way. Now, one thing is, for example, in this derivation at least, I use the commutation relations between the momentum and the fields. So what are the momentum corresponding to my fields? Let's say, let me call this the canonical momentum for the field A mu. Well, how do you calculate this canonical momentum? I take derivative of my Lagrangian with respect to the time derivative of the field A mu. Well, this is my Lagrangian. Now, let me ask you this question. What is the canonical momentum corresponding to A0? Well, this will be del 0 A0. But my Lagrangian doesn't have del 0 A0 in it. So A0 field doesn't have a canonical momentum. So that was one of the most serious mistakes we did. So this is what's called, as your friend was trying to say, this is actually a constraint that we should satisfy. The A0 field doesn't have a momentum. Now, quantizing such constrained systems can become cumbersome. As you had seen over here, I calculated a propagator which didn't really work. What did I do? I tried to apply the operator that my field satisfies on this 2-point function. You see, there are 2 things I skipped. One was that here, what do you do with these commutation relationships? Practically, they don't exist. There is no, for example, if nu is 0, that's not the canonical momentum. So I cannot really use that. But still, you see here when I wrote it in this form, I basically identified 3 fields. These 3 fields are AKIs. For each K, there are 3 fields. Those are AKI, epsilon mu K. Those are the fields I have in momentum space. They are easier to identify. Those fields still satisfy the canonical commutation relationships. So you should actually go to these definitions. We had already solved our constraints in these definitions. Remember, by saying that A mu I K, it only has 3 fields. In the rest frame of K, these are the 3 fields we have. Then you can just use these. Essentially, if you remember classical mechanics, when you have constraints, what you do, you solve for constraints, obtain generalized coordinates which don't have any constraints, and then you just work with them. Well, basically over here, these fields, these annihilation creation operators do not have any constraints anymore. There are 3 of them. Epsilon mu i's, they are already solutions of my constraint equations. But of course, then you will have another problem. You will, I do strongly advise you to calculate that. You will need to calculate epsilon mu star for the same momentum. Sum over I. You will have to carry out such summations. So, what can I say about the general form of this, the result of this summation?
It's
Yes.
symmetric. Symmetric. No.
No, it's not necessarily symmetric. But you see, what do I know? I know that it has 2 Lorentz indices, and it depends on K. It has to be a rank 2 tensor. So, the same argument, A G mu nu plus B K mu K nu. This is the general form of that summation. Now, I still need to determine A and B. Let me multiply both sides by K mu. And remember, epsilon mu, these are i's. I goes from 1 to 3. Remember, K mu multiplied with epsilon mu I is 0 for each I. So this should be 0. But it is, from the left-hand side, it is 0. If I look at the right-hand side, I will see that this is K nu plus B K squared K nu, which tells me that A is actually minus B times K squared. So this is one condition I have.
We also know that when mu and mu are equal because of the normalization condition.
That is, when you multiply by G mu nu, both sides, that will give me another equation. I is equal to 1 to 3 epsilon mu I epsilon I mu star should be equal to 4A plus BK squared. But this, as your friend pointed out, by normalization of these epsilon field is minus 1. So the left-hand side is minus 3, because for each I it is minus 1. I am summing over I from 1 to 3, so the left-hand side is minus 3. Well, the right-hand side is minus 3bk squared, which tells me that b should be equal to 1. And I is equal to 1 to 3 epsilon mu I k epsilon mu I star k turns out to be, well, if b is 1, a is minus k squared g mu nu plus k mu k nu.
Is it B 1 over K squared? No? 1.
No, sorry, b is 1 over k
1 over
squared.
K
Yeah.
squared.
And when you calculate the propagator, what you will get is p squared. That's the main difference. So the lesson is, first solve your constraints. At least that is one way of working with these things. Solve your constraints and then deal with the equations, with the fields that don't have your constraints. So any questions?
As far as I remember, there are two types of constraints. For example, in this example, when we take the partial derivative of the equation of motion, we have a first order constraint. For example, the constraint that needs to be satisfied by P is a second order constraint.
I don't remember that now.
Because I think it depends on which type of constraint we have. It doesn't apply for all constraints.
Do you remember the first order, second order constraints from your classical or analytical mechanics courses? You see, the idea is, let's say that del mu a mu is equal to 0. I have such a constraint.
There
Okay.
was stuff like holomorphic, nomomorphic particles.
Well, I don't remember. I'm bad at names. But what I remember is, let's say this is a constraint. I can impose this constraint at a given time. But that doesn't guarantee me that it will stay as the same constraint. I have my Hamiltonian should also commute with this object. But it need not. If it doesn't commute with my Hamiltonian, that is my second constraint. Whatever the result of that commutator is, should also be 0. That's another constraint that I have to impose on my system. Well, that thing, whatever that is, should itself commute with the Hamiltonian. If I don't exactly get 0 for that commutator, that's my third constraint. So you can just, from one constraint, in order to be able to impose that constraint at all times, you can just generate all kinds of constraints that you like. But at least in this case, I know that this solution over here satisfies my constraints at all times. So I'm happy with working with the fields epsilon mu ik. Those are my momentum space fields, and I'm done. You see, there was one thing else we could have done. You see, del mu a mu is equal to del 0 a0 minus the gradient of a. We had already seen that a0 doesn't have a momentum. So a0 is kind of problematic. Well, let me solve for a0. This is just a solution of that equation. Well, then put this a0 in your Lagrangian. You see, that's also what you do in classical physics. You have, let's say, if you have a particle moving on a loop, on a circle, you don't work with x and y coordinates. You just solve your equations, come up with some other parameters, and work with those other parameters. Now the same thing over here. There's a constraint. I can solve that constraint equation, at least ideally. But then, you see, 1 over del 0 is basically like a Green's function for time evolution. Well, a Green's function is a non-local operation. The value of the field over here depends on the value at some other point. So this is, let's say, non-local in time. The solution for a0 will be non-local in time. I can express it in terms of the vector components, but it will be a non-local expression. So if I substitute this a0 into my Lagrangian and try to work with the remaining 3 degrees of freedom, my theory will look as if it is non-local in time. But at the end of the day, if you calculate anything, they will always be local in time. The theory is still local in time. There is no non-locality here. But if you, well, this is one approach to solving my constraint. I solve my constraint, put it in my Lagrangian, work with whatever remains. But then my theory doesn't look local. We will see other cases in gauge symmetry also. Again, I will just come back to my claim that what we are doing here is just drawing some picture. You can have many different pictures representing the same physics. So I see here, if you solve for your constraint, put it in your Lagrangian, and work with that Lagrangian, the picture you draw, you will look as if it is non-local, but at the end of the day, everything will be local. Okay, we will do another example of this. I will discuss another example of this when we do massless case. In the next hour. For example, if you remember Coulomb gauge from electromagnetism. In Coulomb gauge, potential is instantaneous. Whatever change you have of charges over here, the potential here changes instantaneously. Don't just shake your head. I mean, doesn't it violate Einstein's theory of relativity? A change propagates instantaneously. Yeah, the change in potential propagates instantaneously, but what you can measure will propagate at the speed of light. Of course, it won't be apparent in your expression of the potential, but when you actually do real computation, you will see that the changes in anything measurable will propagate at the speed of light. So you have one picture where certain symmetries, certain properties might not be obvious, but in other pictures they will be obvious, and we usually stick with the ones that keep the symmetries obvious. Like, I'm not following this strategy, eliminating one of the fields. I'm still working with this A mu as if there are 4 fields, but I know that there are no 4 fields, there are just 3 of them. And once I move from A mu's to A k's, I have already solved my constraints because of the properties of epsilon mu's, etc. So I will be dealing with those fields.
I don't understand. I mean, you say instantaneously it changes, but you know the information has to transform with the speed of light.
Okay.
I mean,
How will you measure the change in the potential?
if I measure the electric field,
The electric field will change with the speed of light.
okay. Then.
The negative operator is also a vector.
No, it's not a vector.
I mean, how am I supposed to know that the potential instantaneously change that? I mean, I just measured the electric field.
Wait for the next hour.